Hello, welcome to my talk, 4 bytes of power. I will tell you about exploiting CVE-2021-26708 in the Linux kernel. My name is Alexander Popov. I'm Linux kernel developer since 2013, and I'm security researcher in Positive Technologies. The plan of the talk. First, I will give the overview of this vulnerability, the bugs and fixes, and disclosure procedure. Then I will focus on exploitation of this vulnerability for x86-64. Hitting the race condition, 4 bytes memory corruption, and the long way how to turn this memory corruption into full arbitrary read and write. Then I will show the exploit demo for Fedora 33 server. The exploit will bypass SMEP and SMAP platform protections, and I will tell about possible exploit mitigations. First, the overview of the vulnerability. It is a local privilege escalation in Linux kernel. The type of a bug is race condition. Actually, it is 5 similar bugs in virtual sockets of the Linux kernel. Moreover, major Linux distributions ship this functionality as kernel modules. About the attack surface. The vulnerable modules are automatically loaded. To do that, you just create a socket for this specific domain, and it is available for unprivileged users. Moreover, username spaces are not needed for that. It is cool. I used the syscaller kernel fuzzer with some custom modifications, and it gave kernel address sanitizer report, the kernel crash, on virt.io transport notify buffer size function. But somehow the fuzzer failed to reproduce this bug, and so I inspected the source code and developed the reproducer myself. Let's look at the code. Here you see several variables declared and then initialized, and after that the socket lock is acquired. But that is strange. Why in that order? The transport for virtual socket may change when the lock is not acquired. In that case, the local variable value becomes out of date, and that is an obvious race condition bug. I found 5 similar bugs in the whole source code file, and it looked like intentional. That is strange. But searching the Git history helped to understand the reason. Initially, the transport for virtual socket was not able to change, but then bugs were implicitly introduced in November 2019 when virtual socket multi-transport support was added. And fixing this vulnerability is trivial. We simply initialize transport local variable after lock-sock. Now about the timeline. As I said, the vulnerabilities were introduced in November 2019. And on the 7th of January this year, my custom syscaller got a crash. After Christmas holidays, I started to investigate this vulnerability, and 2.5 weeks later, I got a working proof of concept exploit and the fixing patch. I sent the crasher and patch to security@kernel.org to perform the responsible disclosure procedure, and the patch review started. I got very prompt replies from Linus Torvalds and Greg Kroah-Hartman. We concluded on the following procedure. First, sending the patch to the Linux kernel mailing list in public. Then, merge it to upstream and backporting to the affected stable trees. Then, informing the Linux distributions via Linux distros mailing list. And finally, disclosing the security relevance of this issue at the public mailing list when Linux distributions allow me. In fact, the first step is questionable. Linus decided to merge my patch without any disclosure embargo. That is what he told. This patch doesn't look all that different from the kinds of patches we do every day. I obeyed and proposed that I should send the patch to the mailing list in public, because anybody can filter vulnerability fixes as commits that was not discussed in public mailing lists. So on 2nd of February, the second version of my patch was merged into upstream, And 2 days later, Greg backported it to affected stable trees. I informed Linux distributions via Linux distros mailing list and asked how much time do they need before I make the public disclosure. And I got quite strange reply, which I was not prepared to. If the page is committed to upstream, then the issue is public. Please send to OSS security immediately. I was confused, but made the public disclosure. You can see the link here. And on next day, CVE-2021-26708 was assigned to this issue. Some thoughts about disclosure procedure. The question is rising, is this merged as soon as possible procedure compatible with the Linux distros mailing list? I'm not sure. As counterexample is how I reported the vulnerability for the Linux kernel back in 2017. First, Case Cook and Greg organized 1 week disclosure embargo. Next, Linux distributions from the Linux distros mailing list integrated my fix into their security updates without any rush. And when the disclosure embargo was ended, security updates were published synchronously. Very good. You can see more info in the article about this vulnerability. That was about the mistake in the code. Now about the memory corruption. How to provoke this race condition. I exploited the bug in virtual socket stream setsocopt. Reproducing it requires 2 threads. In first one, we should call setsocopt, which sets the size of virtual socket buffer. And the second thread should simultaneously change the socket transport. It performs reconnecting to the virtual socket, and meanwhile, the setsocopt is trying to acquire the lock. That is the full picture of the race condition. The first thread locked the socket before the second one. That's why the second one is waiting, while the first one is performing work. And the first one frees Virtio virtual socket structure and sets the transport to null, then releases the socket. At this moment, the second thread gets the ability to proceed the work, but it uses the transport variable, which is already out of date, and calls Virtio transport notify buffer size, the function where I got the crash. And in this function, the attacker controlled value is written to buff alloc field of the Virtio virtual socket structure. That's how using out-of-date value from a local variable looks like. Now about the memory corruption. We have write after free to Virtio vsoc soc object. The size of this object is 64 bytes. It lives in general kmalloc 64 slab cache, which is good for exploitation. The buff alloc field is 4 bytes in size, and it resides at offset 40. So the value controlled by the attacker is written to this buff alloc field. In other words, 4 bytes controlled by the attacker are written to the freed memory. Now about fuzzing miracle. As I said, Syscaller didn't manage to reproduce this crash, and I had to develop the reproducer manually. But why did fuzzer fail to do that? Looking at the code gives the answer. Here we see that the notify buffer size handler is only called when the value given to setsocopt is different from the previous one. So for memory corruption, setsocopt should be called with different buffer size value each time. And that is the fun hack that I used in my first reproducer to get that. Here you can see that I call clockGetTime, take the number of nanoseconds as size, and use it in setsocopt. That makes setsocopt be called with different buffer size each time. The upstream syscaller doesn't do things like that. It chooses the syscall parameters when the fuzzing inputs are generated. And later, when inputs are executed on the target, they don't change. So I still don't completely understand how fuzzer generated this crash. I think it did some lucky multi-threaded magic with the virtual socket buffer size limits, but then failed to reproduce it. Now about the exploitation of this vulnerability step by step. I've chosen Fedora 33 server as exploitation target, and it has the kernel 5.10.11. And from the beginning, I had a goal to bypass SMEP and SMAP, which stands for Superuser Mode Execution Prevention and Access Protection. Those are x86-64 platform defenses which prevent executing user space code in the kernel and dereferencing user space pointer from the kernel. And of course, bypassing kernel address space layout randomization was included in my goal. As I mentioned, this vulnerability gives write after free of 4-byte controlled value to a 64-byte kernel object at offset 40. That is quite limited memory corruption, and I had really hard time turning it into a powerful weapon. By the way, in this presentation I use the photos of artifacts from the Hermitage Russian State Museum. I really love this museum and recommend you visit it. I started to work on stable heap spraying. The exploit should perform some user space activity that makes the kernel allocate another 64-byte kernel object at the location of freed object. In that case, 4-byte write after free corrupts the sprayed object instead of memory which is marked as free. First, I made some experimental spraying with addKey syscall. I called addKey several times after the second connect, while the setsocopt is trying to corrupt the memory in parallel in the second thread. And ftrace allowed me to confirm that freed memory is overwritten. And I saw that successful heap spraying is possible. The next step was choosing another 64-byte object that can provide a stronger exploit primitive when it has 4 corrupted bytes at offset 40. And that is not so easy. At first, I tried the IOVEC technique from Bedbinder exploit by Maddie Stone and Jan Horn. The main idea is a carefully corrupted IOVEC object can provide arbitrary reading and writing of kernel memory. But this idea failed. There were 3 reasons for that. First, the 64 IOVEC is allocated on kernel stack instead of heap. That is bad. Second, 4 bytes at offset 40 override the IOVEC length instead of IOVEC base, so the original technique for arbitrary read-write can't work. And finally, I found out that this IOVEC exploitation trick is dead since kernel version 4.13. Awesome Alviro killed it back in 2017 in the commit where he moved the checks of IOVEC from the IOVEC creation to IOVEC memory copying. So now this exploit technique doesn't provide you arbitrary read and write anymore. I had very exhausting experiments with various kernel objects suitable for heap spraying, and I was very glad to find message send, finally, that creates this structure, MSG, in the kernel space, and you can see the output of Pahol utility for this structure. When you create the message buffer with 16-byte message text in the user space, the kernel creates such an object in the kmalloc 64 slab cache, which is like our freed object. So it is very nice for heap spraying. And this 4-byte write after free corrupts the security pointer at offset 40. Jokingly, I used this security field to break Linux kernel security. Okay, this security field points to the kernel data allocated by Linux security modules. In case of Fedora, it is used in SE Linux. And this kernel data is freed by security MSG free function when the message is received in the user space. Corrupting 4 least significant bytes of this security pointer provides arbitrary free, which is a much stronger exploit primitive. Okay, we have arbitrary free, and where to aim? After achieving arbitrary free, I started to think what to free with it. And here I used the same trick as from my previous exploit. Second, connect to a virtual socket calls the assign transport function. That sets the socket transport to null, and the simultaneous setsocopt triggers the kernel warning. It happens when this var.io transport send packet info is called just after use after free. And the exploit can parse the kernel log and extract interesting information from this kernel warning. Here you can see how this kernel warning looks like. It contains a lot of interesting information. A quick debugging session with GDB showed that the RCX register contains the kernel address of the freed structure, virt.io vsoc, and the RBX register contains the kernel address of the virtual socket structure itself. On Fedora, unprivileged users can open and parse the kernel log. So if one more warning arrives to the kernel log, we understand that exploit won one additional race. And we can parse the log and get addresses from these registers. So now we have kernel infoleak exploit primitive and we can see the kernel pointers. My further exploitation plan was to use arbitrary free for use after free. First, free some object at the address which is known from the kernel log. Then perform heap spraying to override this address with control data and get more power with this corrupted object. Using arbitrary free for virtual socket object address from RBX register is useless, because this object lives in a dedicated slab cache where I can't do heap spraying. So I invented how to exploit use after free on MSG, which address we have in RCX register. For overwriting MSG, I used wonderful setxutter and userfaultfd heap spraying technique, which is developed and published by Vitaly Nikolenko. This diagram shows how to perform arbitrary read with MSG kernel object.
On the left, we see the original MSG structure. The first field, called mlist, points to the next element in the system5 message queue. The second field, mtype, stores 1. The third field, called mts, stores the size of the message data. As I mentioned, it is 16, so the MSG kernel object is allocated in kmalloc 64 slab cache. The following structure field, called next, is the pointer to the first message segment. The kernel implementation of system5 message reserves around 4000 bytes for message data, and if we send a bigger message from the user space, the remainder is saved in the list of message segments. In this original MSG, there is no message segments, so this field is null. And the last structure field, called security, points to SE Linux data area. And now on the right you can see the overwritten MSG object that I used for arbitrary read. The mlist field is overwritten by some dummy value, since I don't know a valid address for this field. And the message type is set to lead to help the exploit debugging. The MTS field that stores the size of the message now stores 6096. That is enough for one message object and one segment object. The next field, that previously contained null, is overwritten by the kernel address that we want to read from. And here we pretend that this arbitrary reading is just a handling of the message segment. And please note that I don't override MSG security to avoid breaking SE Linux permission checks. That is possible with this wonderful setxutter and userfaultfd technique that I mentioned. The secret is that I place the spraying payload at the border of the page faulting memory region, so that copy from user hangs just before overwriting MSG security.
Receiving this crafted MSG manipulates the system5 message queue. And unfortunately that breaks the kernel and provokes the kernel crash because the mlist pointer is invalid. But the MSG receive documentation allowed to find the solution. There is a flag which is called MSG copy. That flag allows to fetch a copy of the message without changing the message queue, so do it non-destructively. As a result, we have arbitrary read exploit primitive. Let's use it for some interesting kernel memory. Okay, how to exploit arbitrary read? First, we need to get the address of some good message object. We win the race on the virtual socket and then spray the message after the memory corruption. When we parse the kernel log, we extract this address of the good message from the RCX register and also save the kernel address of the virtual socket object from the RBX register.
To do that, I use 4 least significant bytes of the address of good message as the buffer size in setsocopt, and this value is used for memory corruption when the exploit wins the race. And this time we call message send right after the second connect. So the message object is placed at the location of the freed object and message object is corrupted. As you can see on the diagram, now security pointer of the corrupted message stores the address of the good message. And if the memory corruption of the security field of the message object happens during the message send handling, then SE Linux permission check fails. And in that case, message send returns -1 and the corrupted message is destroyed. So freeing the security data of the corrupted message actually frees the good message. And we can override it.
Okay, the good message is freed and we can override it with heap spraying.
Right after the failed message send system call, the exploit calls pthread barrier wait, which wakes 127 spraying pthreads, and these pthreads call setexcr and override the freed message with the controlled data. Now mlist and type fields contain the dummy values, and the size contains 6096, which means that the message has segments, and the next pointer stores the address of the virtual socket object, because we want to read the contents of this object to the user space for mounting the further attack.
Okay, now we can read the contents of the virtual socket object to the user space simply by receiving this good message with the message receive function. Here you can see the flags which I used for message receive. And we have this virtual socket data in the user space. Let's look what's inside. That's what I found inside the virtual socket kernel object. First, plenty of pointers to objects from dedicated slab caches. That is not interesting for exploitation. I don't know how to use it. Second, the pointer to memcgroup object. It is a big, interesting structure which is allocated in the kmalloc 4K slab cache. And I tried to use arbitrary free against this structure, but unfortunately kernel panicked instantly. So it looks like this object is used by the kernel very intensively. Next, the pointer to kernel credentials. That is the data which I need to override for privilege escalation. It's a pity, but this object lives in a dedicated slab cache, so freeing it and spraying to override it can't work. Finally, I found the socket write space function pointer at offset 688, and it is set to some address of a known kernel function, so I can calculate the kernel address space layout randomization offset, which is nice. As I mentioned, use after free on memcgroup didn't work, and I started to think, what can I do? And I decided to employ my old trick from the exploit from 2017. In that exploit, I turned double free on kmalloc 8k object to use after free on socket buffer, and I decided to repeat that trick. Network-related buffers in the Linux kernel are represented by socket buffer object. This object has skb shared info structure, which contains destructor arg pointer. That pointer is very nice for control flow hijack. Creating a 2800 byte network packet in the user space makes skb shared info be allocated in kmalloc 4k slab cache. It is where our memcgroup object lives. And that's how I exploited use after free on skbuff. First, I created one client socket and 32 server socket. And I sent this 2800 byte buffer to each server socket. I filled the buffer with 42 in hex to check it later. I performed arbitrary read for virtual socket object and extracted the pointer to memc group. Then I calculated the possible socket buffer address by adding 4K to memc group address. And I performed arbitrary read for that possible skbuff address. And if I find those 42 which I wrote to the network packet, that means that I found this skbuff object in the kernel space. Otherwise, I can add 4096 to possible skbuff address and try again, arbitrary reading and checking the contents. When I found the skbuff object in the kernel space, I can do arbitrary free against it and override the contents of the socket buffer with the controlled data using heap spraying. On this diagram, you can see the overwritten contents of the socket buffer. At the bottom, we see the skb shared info structure with destructor arg pointer, which points to ubuff-info residing inside the network buffer. I can do that because I know the kernel address of socket buffer, and the ubuff-info structure contains the callback pointer and the descriptor, which is unsigned integer. Now about the callback pointer and control flow hijack. Actually, I didn't manage to find a stack pivoting gadget in this VM Linux kernel image that can work in my special restrictions. So I invented the arbitrary write primitive that can work in one shot with one gadget. It bypasses SMEP and SMAP because I don't dereference any user space address. Here on the slide, you can see the code that prepares the payload with this gadget. It is quite complex. I will try to explain it step by step. First, about the state of CPU registers. RDI stores address of ubuff-info. In other words, it is the address of our payload. RCX stores 0 and RSI stores 1. RDI plus 8 points to ubuff-info desk, where I store the address of kernel credentials with the offset of effective user ID and effective group ID. The gadget moves 8 bytes from RDI plus 8 address to RDX. In other words, it moves the address of effective user ID and group ID into RDX register. And the next instruction in the gadget moves RSI value, which is 1, to the address in RDX. RCX is 0, so adding RCX value to RDX doesn't matter. So 1 from RSI is written to effective user ID and group ID. And that's why I decrement the desk pointer to 1, because I want this 1 value from RSI get outside of user ID and group ID. Okay, and we have this arbitrary write exploit primitive, which uses skb shared info and writes zeros. It's quite weird, but it works. To have root privileges, we need to write zeros to effective user ID and group ID, and then to normal user ID and group ID. And then game is over, we have root. Now demo time. That is the exploit demo. You see Fedora 33 server in a virtual machine. First I show the system characteristics. Here you see kernel release name, kernel version, command line, platform features, and user ID. Now I'm starting the exploit. Let's stop it and look at it in details. We begin as unprivileged user and first collect good MSG locations, as I described. Then we perform arbitrary free for good message using corrupted message. Overwriting good message with controlled payload allows us to perform stage 3 arbitrary read of virtual socket object using this message. Arbitrary reading allows to get memcgroup pointer, kernel credentials pointer, and calculating kernel address layout randomization offset. Stage 4, we search sprayed socket buffer near memcgroup. I continue the video. Okay, we found a real socket buffer, and now perform use after free against it. Get root, and let me show the video from the start again. Here I show that we are root and party hard. Okay, we saw how exploit worked, and now let's talk about possible exploit mitigations. First, I want to tell that exploiting this vulnerability is impossible with Linux kernel heap quarantine. That is because this memory corruption happens very shortly after the race condition. So we don't have time to overflow the quarantine with new allocations. You can read the story about my slab quarantine prototype in this article. Here there is a link. Next, the mod harden from jar security patch can help against kernel module automatic loading by unprivileged users. Setting unprivileged user fault FD to 0 can help against user fault FD abuse, which I used for kernel heap spraying. Setting dmask restrict to 1 can help against info leak via the kernel log. Control flow integrity technologies can prevent calling my ROP gadget. You can see them listed in my Linux kernel defense map. Hopefully, in future, ARM memory tagging extension will help against use after free bugs on ARM platforms. Finally, I heard some rumors that there is a jar security Wunderwaffe called AutoSlab, which can help against my heap spraying technique which I used in this exploit. However, we don't know much about it. Finally, the conclusion. Investigating and fixing this vulnerability, developing the proof of concept exploit, and preparing this talk was a very big deal for me. I hope you really enjoyed it. I managed to turn the race condition with very limited memory corruption into full power arbitrary read-write for kernel memory. Very soon I will publish a large and detailed write-up about this exploit. Thanks for your attention. This conference is online, so send me your questions. I'm glad to answer.